Have you ever pondered the enigma of prime numbers, those solitary figures that only divide by one and themselves? These mathematical marvels have been captivating the minds of scholars for over 2,300 years, ever since Euclid, the Greek mathematician, first established their infinite existence. Let's take a moment to revisit the basics. Prime numbers are unique because they only have two distinct positive divisors, one and themselves. Take the number 3, for instance. It's a prime number because it can only be divided evenly by 3 and 1. But if we consider the number 4, it's not a prime because it can be divided by 2 as well. Now you might be wondering, why do these numbers matter? Well, prime numbers are often referred to as the building blocks of all natural numbers. You can reach any number by multiplying prime numbers together. For example, 15 is the product of the prime numbers 3 and 5. And 50, it's simply 2 times 5 times 5. The pattern continues indefinitely, proving that you can reach any number through a multiplication process involving prime numbers. However, the fascination with prime numbers extends beyond their basic definition and function. The true enigma lies in their distribution. If you start counting 1, 2, 3, 4, and so forth, and stumble upon a prime number, there's no formula that can predict where the next one will appear. Their randomness is what makes them so intriguing and elusive. Yet, despite their unpredictable nature, formulas do exist that can generate prime numbers under certain conditions. The most famous of these is n2 plus n plus 41, which generates prime numbers for each value of n from 0 to 39. But beyond that range it falls short. And as we know, there are infinite prime numbers. Prime numbers, infinite and unpredictable, hold a certain charm that has intrigued mathematicians for centuries. Their solitary nature, their role as the building blocks of all numbers, and their elusive distribution pattern make them a captivating subject of study, a mathematical mystery waiting to be solved. The Greek mathematician Euclid, over 2,300 years ago, proved an astounding fact. The quantity of prime numbers is infinite. Now let's unpack this statement a bit. The concept of infinity is a tricky one. When we say that something is infinite, we essentially mean that it has no end. It keeps going on and on, forever. This is precisely what Euclid discovered about prime numbers. There's no last prime number. You can always find another one. Euclid's proof of this was beautifully simple. He argued that if you took any list of prime numbers, no matter how long, and multiplied them together before adding one to the result, you'd get a new number that couldn't be divided evenly by any primes on your list. As such, this new number must either be prime itself or have prime factors that weren't on your original list. In either case, it shows that there's always another prime number to find. This discovery of Euclid's is monumental in the world of mathematics. Prime numbers are the atoms of arithmetic, the building blocks from which all other numbers are made. To know that there are infinite primes is to know that there are infinite possibilities for creating new numbers. But here's the catch. While we know that there are infinite primes, we don't know where to find them all. It's like knowing that there are countless stars in the universe, but not knowing where each star is located. In the vast expanse of numbers, prime numbers pop up unpredictably. There's no formula that can tell us exactly where the next prime will be. Each prime number is a new discovery, a surprise waiting to be found. So the next time you come across a prime number, give a little nod to Euclid, the ancient Greek, who showed us that there's always another prime number to find in the infinite ocean of numbers. In the infinite sea of numbers, prime numbers sporadically appear, their locations unpredictable. The mystery of prime numbers lies in their distribution. Where is the next prime number? This is a question with no definitive answer. The unpredictable nature of primes, their refusal to adhere to a set pattern, is what makes them so intriguing. You see, if we take a series of natural numbers, say 1, 2, 3, 4, and so forth, and we find a prime number in this series, we can't precisely predict where the next one will show up. It's like trying to predict the next winning lottery number. It's practically impossible, and that's precisely the enigma of prime number distribution. This unpredictability, however, doesn't mean there aren't formulas to generate prime numbers. There are, but these formulas are not infallible. They don't work in all cases. They're like a weather forecast. They can predict with a certain degree of accuracy, but they can't guarantee. Take the most famous one, for instance, n2 plus n plus 41. This formula generates prime numbers for each value of n from 0 to 39. Replace n with 1, and you get 43, a prime number. Replace it with 22, and you get 547, also prime. But beyond 39, this formula falls apart. It no longer generates prime numbers. So, we have these formulas, yes, but none that works for all numbers. None that can predict the distribution of prime numbers throughout the entire infinite series of natural numbers. It's this seemingly random scatter of primes, this lack of a discernible pattern, that has both baffled and fascinated mathematicians for centuries. Despite the brilliant minds and sophisticated technology at our disposal, the prime numbers hold on to their secret. The unpredictability of prime numbers, their refusal to follow a pattern, remains one of the most tantalizing puzzles in mathematics. While there is no universal formula for generating prime numbers, there are formulas that work in certain cases. One of the well-known formulas is the one that goes like this: n squared plus n plus 41. This formula has an interesting property. It generates prime numbers for each value of n, starting from 0 all the way up to 39. Let's take a closer look. When you substitute n with 0, the formula gives us 41, which is a prime number. If you replace n with 1, you get 43, another prime. And the pattern continues. For instance, substituting n with 22, we get 547, also a prime number. So, for a stretch of 40 values, this formula works like a charm, churning out prime numbers as if they were on a conveyor belt. It's like a magic trick, where every wave of the wand, or in this case, every increment of n, reveals a new prime number. However, the magic doesn't last forever. As we move past 39, the formula's prime-generating abilities falter. When n hits 40, the output is not a prime number anymore. It's 1681, which can be divided by 41 and 41 squared, hence breaking the prime number rule. This limitation isn't unique to this formula alone. There are other formulas too, which generate prime numbers in certain ranges, but stumble as the numbers get larger. It's like climbing a mountain that has no peak. Every time you think you've reached the top, a new, higher peak appears in the distance. These formulas are fascinating. They're like a torchlight that illuminates a small patch in the vast darkness of the prime number world. But they're not enough to map out the entire landscape. We've been studying prime numbers for over 2,300 years, and yet, a significant part of their mystery remains unsolved. These formulas, fascinating as they are, only provide a glimpse into the vast, uncharted territory of prime numbers. The mystery of prime numbers is not just a mathematical curiosity, it has serious implications for our world. Let's take a moment to consider the potential consequences of cracking the prime number distribution mystery. The implications are far-reaching, and the stakes are incredibly high. You see, prime numbers are not just the building blocks of natural numbers, they are also the foundation of modern cryptography. Cryptography, in layman's terms, is the art of secure communication. It's what keeps our emails, bank transactions, and other digital communications safe from prying eyes. At the heart of this security is the process of encryption, which involves transforming data into a format that only someone with a special key can read. And guess what? This process relies heavily on the properties of prime numbers. So imagine if someone were to discover a formula that could predict the distribution of prime numbers. This person could, theoretically, crack any encrypted message. That's right, any message. From your online banking details to state secrets, nothing would be safe. The potential for misuse of this information is staggering. It could lead to a collapse of the global financial system, the exposure of state secrets, and the erosion of individual privacy. In a world where data is the new gold, such a breakthrough would be akin to acquiring the master key to every vault. But before you start worrying, it's important to remember that this is a problem mathematicians have been wrestling with for over 2,300 years. And despite the advances in technology and the combined efforts of the brightest minds, we are still no closer to solving it. So while the threat is real, it is also highly unlikely. But it serves as a reminder of the power and importance of prime numbers, not just in mathematics, but in our everyday lives. The mystery of prime numbers, then, is a mystery with high stakes, a puzzle whose solution could reshape our world.